In these 4 seconds, 100 kilos of textiles were thrown away in Australia. Over a year, this amounts to more than 800 million kilos of textiles dumped in Australia alone. Of all the textiles we throw away, only 7% is captured and recycled, making it by far the worst waste stream in terms of recovery rate in our country. Not plastic waste, not food waste, but textile waste. This has a devastating impact on both our marine and land environments, contributing to 20% of global water pollution and 10% of global carbon emissions. This is why we at Enactus Australia set out to solve the Australian textile waste crisis. My name is Raghav. I'm joined by Emma, Amna, and Jessie, and we're here to present our startup, Circle.
Our mission started with an obsession to learn as much about the problem as possible. We wanted to make sure that we were targeting the core issue and not just treating a symptom. And so we started at the epicenter of textile recovery efforts in Australia, charity shops. We conducted over 80 interviews, from volunteers to the CEO of Salvos, basically anyone that would pick up the phone and help us learn. But we soon uncovered a shocking truth. Only 15% of textiles that charity shops receive can be reused again. The remaining 85% are at the end of their lives and destined for landfill. We began to understand that something deeper was going on. And so after speaking to repair shops, upcyclers, councils, and textile manufacturers, we identified our first key insight. In Australia, all end-of-life textiles are destined for landfill.
We wanted to dig deeper to figure out what was going wrong. Why can't our textile recovery efforts do anything about an end-of-life textile? We soon discovered a common flaw. All of our textile recovery efforts are focused on making the textile serve its original purpose as a fabric for as long as possible. This overlooks a crucial problem. Fabrics degrade over time. Eventually they reach a point where they can no longer be usable. Whilst old jeans might be useful as a tote bag or a shrunken t-shirt can become a rag, ultimately they will end their life as a fabric. This was our second key insight. All current solutions focus on making textiles last longer as fabrics, where they eventually degrade and end up in landfill.
So how do we overcome this? Whilst textiles at the end of their life are no longer valuable when viewed as a fabric, they're incredibly valuable when viewed as a resource. Think of the clothes in your wardrobe: cotton, wool, silk, polyester. These are incredibly valuable resources when used as the input for new products. This was our third and final key insight, that Australian textile waste is a valuable resource goldmine. We had to develop a solution that didn't view textiles as fabrics, but viewed them as a resource. We had to build a solution that didn't just extend the life of textiles, but gave them an entirely new life.
So with all these insights in mind, we needed a solution that was able to break down a textile into its fundamental materials in order to rebuild it again into something new. And this, we realized, is only possible with a chemical process. So we partnered with the BioPre Institute, a chemical engineering center at Monash University, to help us interrogate several chemical recycling technologies. Our scientific journey began in early 2022, where we tried to turn textiles back into fiber. However, as we progressed in our research, we realized the unit economics of this process simply did not add up, and there were other technical barriers to achieving this process. This meant we couldn't build a truly revolutionary business with this as our core solution. So after many sleepless nights, pivots, and failed experiments, we finally landed on what we believe is a groundbreaking innovation. I'm proud to present C-Plast. C-Plast is a groundbreaking innovation that turns cotton and cotton polyester blended textiles into biodegradable plastic.
Our technology can be broken down into 3 main processes: dissolving, regenerating, and bioplastic production. We start with our textile and combine it with an environmentally friendly and reusable type of liquid called an ionic liquid. When this powerful dissolving agent interacts with the fabric, the fibers break apart, dissolving it and preparing it for the second stage of our process. With mixed blend fabrics, this process selectively dissolves the cotton, leaving the polyester as an undissolved solid, which can then be recovered and recycled.
In the second part of our process, we then manipulate this dissolved mixture and subject it to various conditions in order to regenerate it and give it a new structure. What once was a fabric has now taken a form that can be used to create our product.
Finally, we further process this regenerated material to produce our bioplastic. With a slight tweak in production methods, we are able to create a bioplastic with significantly different properties. For example, heat pressing creates an extremely rigid and sturdy material, whereas simple UV exposure produces a bendable bioplastic.
So now that you understand our process, let's discuss what makes CPlast so incredibly groundbreaking. We've developed a way to continuously reuse our input ionic liquid such that we can exponentially decrease our operating cost. Using a simple liquid separation technique, we can recover nearly all of the input ionic liquid without losing any of its potency. In the lab, we've shown this reuse rate to be 93%. But what does this mean? Well, if we follow the math, a typical ionic liquid costs around $2,500 per kilogram. After 10 iterations of our process, we can bring this cost to below $300 per kilogram, and after 50 iterations, we can bring this cost to around $60 per kilogram. That's a 98% reduction in input cost, all as a function of our revolutionary process. This is what gets us so excited about CPlast.
Our second game changer is our ability to recycle mixed blend fabrics. This process allows us to recover and recycle up to 75% of all textile waste in Australia, enabling us to truly tackle the textile waste crisis.
Our third and final key innovation is our product. Cellulose bioplastics are a category of plastic alternatives that have sparked global interest for two key reasons. The first is their essentially equivalent mechanical properties to traditional plastics. And the second is their particular excellence in high-stress environments, such as extreme temperatures. So, if this material is so good, why don't we see it being used everywhere? Well, bioplastics are held back because of one key commercial obstacle: high production cost. This is because the conventional inputs used for these bioplastics require extensive material sourcing and arduous chemical separation techniques. However, we at Circle are able to leapfrog this financial hurdle through the use and recovery of our ionic liquid. Conventional cellulose bioplastics cost around $3.76 to produce 1 kilogram. But with our initial cost modelling, we project that at scale, we can produce CPlast for a cost of $2.95 for 1 kilogram. This gives us a cost reduction of 22%, priming us to capture a global market opportunity valued at over $2 billion. Our product has already gained some early customer interest, including the global packaging company Aurora. Our business model will seek to serve companies like Aurora by providing them with the bioplastic for them to then further develop into their final product. This initial customer scoping has indicated that we can expect a price point of around $4 for a kilogram of our bioplastic product. This gives us a gross margin of 35%, where we're passing on our cost savings to our customers. And if all that wasn't enough, our product represents a true closed-loop solution, being both fully recyclable and 100% biodegradable.
At this stage, we've completely de-risked all existential threats to CPlast through our rigorous technical testing. You're not just looking at a team with a concept, but a team with a proof of concept that we can conduct CPlast at a laboratory scale. We hope to test the scalability of CPlast in our pilot production. We have $75,000 in grant funding expected to hit in the next 12 months, which will help facilitate the establishment of our own laboratory. And with an intellectual property agreement in place with our current lab, we are primed to take the next big step in our journey.
But this is really just the beginning. Whilst our initial IP protectable solution is used in the production of bioplastics, the underlying solution can be used in applications outside of this. Think hydrogels, aerogels, membranes, films, you name it, our process can create it. And whilst we're confident we can become the renewable leaders in each of these product segments, this isn't enough for us. We don't just want to be the best renewable alternative, we want to be the best product altogether. We don't want to be the paper straw, we want to be the electric vehicle. Now this is all a lot to take in, but if there's anything we want you to take from today's presentation, let it be the following 3 things. Number 1, we're addressing the core root problem at the heart of textile waste, not simply addressing a symptom. Number 2, we've innovated our business model specifically around the cost problem that many waste companies face. And number 3, we're commercially, technically, and legally primed to take our next phase of growth out of the lab. Everything we do at Enactus Australia is built with sustainability in mind, and that's why we address the following 6 key United Nations SDGs. What we're building at Circle gets us so excited about the future, and we hope it gets you excited too. Thank you for listening, and we look forward to taking your questions.
Thank you so much for your presentation. We will start our question and answer period. Please be quiet, keep quiet. Only judges, final time, only judges may ask questions. Please raise your hand if you have a question for the team.
Thank you for the presentation. My question is around the cost reduction, which is the major value proposition that you have highlighted. Now, have you done a kind of simulation to look at how this is sustainable, and when you're expanding the market, has that been done? And if that has been done, what are the prospects? Are we expected to see more cost reduction, or that was what you have presented is the optimal?
Yeah, I'm happy to take that one. So yeah, we definitely, a lot of the time we spent was actually before we even got into the lab, assuming these sort of permutations of different assumptions on reuse rate, recovery rate, all these different things. What does this, what does this business look like at scale, right? And we've done that, and it's a really commercially viable solution. And at scale, these costs only come down as we start to sort of amortize the fixed costs that are associated with producing this solution. So, things like VATs that we need to store the solution. As we scale, we can store more volume per unit of spend on VATs, things like that, right? Because the variable cost is the thing that we innovated on at the beginning and made sure that was kind of our fixed thing that we were innovating along. And so those bigger fixed cost items will sort of over time come down. So yeah, we've definitely spent time looking into that.
Thank you for your presentation. It seems like a really innovative solution for a very big problem. You guys have put a lot of research into this project, but have you guys considered what your break-even analysis is going to be? How much are you going to have to sell in order to cover all of the costs you've spent on research so far?
Sure. So at the moment, we haven't done extensive analysis on what this looks like at scale in terms of selling and buying, because at the moment, we're just in that proof of concept phase where we're looking to really solve those technical questions so we can expand this and take it around the world and really transform how we view end-of-life textiles. So in terms of the break-even analysis, as Jesse mentioned, the main kind of component is that ionic liquid. And as we scale beyond our pilot program to an actual full-scale laboratory, we'll have better numbers on exactly how much our cost is for that core input cost, which is our ionic liquid, and then we can do those kinds of extensive analyses on exactly how much we need to sell, in what markets are the best, and in what countries we want to expand to as well. But at the moment, we're focused on the key kind of technical questions that allow us to then go to that next stage and really make this a worldwide thing.
Thank you for your presentation. I've got 2 questions. The first one being that you mentioned an issue surrounding visiting Chinatown for your preliminary investigations. I'd like to understand how you're going to safeguard against perhaps changes in legislation to do with textiles, since your primary byproduct is your primary product for you to produce C+ is textile or fabric. The second question is, I want to know how much C+ you produced per how much perhaps kgs of fabric.
Yeah, so I'm happy to take the first question there. So your question is around how does our business, what are the threats associated with changes in textile legislation? Yeah, so currently there's a big push from the Australian government. I think it's number 2 on the country's priority list in terms of waste. So they're really pumping a lot of money into this area. So it's actually a positive uptrend as opposed to something that's a risk on the downside. So that's why we're able to make a lot of sort of headway in terms of grant application money. We have this $75,000, and that's really from an initial scan. There's way more money to be had in this area. And textile waste is only getting worse. There's no solution. So we've kind of assumed that the input to our process is almost a foregone conclusion in some sense. There will always be textile waste to be had. Otherwise, it's just getting shipped over to, say, third world countries or developing nations, which can't actually handle that.
And to answer that second question, so the thing with that process is it's essentially one-to-one when the process goes correctly. So 1 kilogram of textiles produces 1 kilogram of this bioplastic product. This is because what we do is we essentially manipulate the cellulose to turn it into a kind of plastic material. So whatever we start with is whatever we end with. Then the other input is our ionic liquid, and the thing with that is that essentially that acts as the thing that changes the cellulose at the molecular structure, but because we can reuse that, it's essentially not even an input in that way. It's almost facilitating that process. So it's one-to-one when the process is going correctly.
It's only 5 more seconds, so no need to ask another question. I'm not going to do it again. Thank you so much for your presentation. Enactus Australia. Thank you. You can leave. I invite you all to stay in the room.